Good afternoon, students. Myself, Shomrat Paul. I am going to present a topic on buck regulator. Or somehow it can be called buck converter. Actually, the name stands for buck. That means the output voltage should be stepped down with respect to input voltage. And for several application purpose in industry, it can be very useful converter with respect to the other converters. So before going into this topic, we should aware of few things regarding buck regulator. See, what is buck regulator? DC converter can be used as switching mode regulator to convert a DC this voltage normally unregulated to a regulated DC output voltage. That means is a kind of converter or regulator through which we can regulate the output voltage. Okay, this regulation is normally achieved by PWM technique, which is called pulse width modulation technique, at a fixed frequency, and the switching device is normally used for, it can be anything that is BJT, MOSFET or IGBT for the purpose of the application. Maybe the high rated frequency is there, or somehow maybe the high blocking voltage will be there. Due on basis of this, we can use type of switch for regulator operation. Okay, fine. In this of basic operation of the chopper, the step down chopper with R load, the output of the output voltage is discontinuous and it contains a huge amount of harmonics. This ripple content normally reduced by the LC filter. There are four basic topologies are normally used for switching regulator, that is buck regulator, that can be boost regulator, buck boost regulator and buck regulator. Today we are going to describe the topic on buck regulator. So as we know, this is a kind of chopper or step down chopper. If you can recall the circuit diagram, the step down chopper, see, this is called the step down chopper, in which we are using only one switch here, that is BJT or transistor, and a load is there. For rectify the unwanted ripples to the output voltage or current, we are using an LC filter here. The remaining are same. And this is a control circuit through which we are giving the appropriate triggering pulse to the transistor or switch, and it is a freewheeling diode. When the inductor tries to discharge or charge, then the freewheeling diode starts conducting. So this is all about for the circuit diagram, and in which that is IS, the small I is defined by the source current, and capital I is, that is average of the source current. I0 IA, that means small I0 defined by the current across the load, and capital IA defined by the average value of the current across the load. Similarly, IC equal to capacitor current, and capital IC is average capacitor current, and IL equal to the current across the inductor, and VC is the voltage across the inductor, and IL, that is the average, that is capital IL, that is average current across inductor. So it can be the total working principle can be defined by two mode operation, mode 1 and mode 2 operation. See, when the switch is in on state, then the current starts flowing through this circuit, right? And when the switch remaining in off state, then the current starts continue due to presence of the inductor. That means what? We can conclude the two mode of operation which is depicted in these two figures. This is mode 1 operation and this is mode 2 operation. See, in mode 1 operation, when the switch remaining closed means the switch is in on state, then the source current IA starts flowing to the capacitor as well as to the inductor, right? Sorry, to the load. Okay, this is mode 1 operation. Now see, when the switch is closed, the switch is open, that means there is no relation to the circuit to the supply voltage. That is why in case of mode 2 operation, when the switch remaining off, there is a no connection with respect to supply. Then this is a circuit diagram which is depicted for the mode 2 operation when maybe the inductor starts discharging to the diode freewheeling diode DM. So the operation can be well defined by the waveforms. Okay. Think the first mode operation can be conducted for the time duration T1 and the second mode operation can be conducted for the time duration of T2. And the second mode of operation conducted for the time duration of T2. When the switch is on, then the current starts flowing to the inductor and to the load. Okay. As the inductor is there, that means current will be gradually increases from its low value to high value as the inductor starts storing energy. That is why the first, suppose this is defined by the voltage difference across the circuit and this is the inductor current. Okay, this is IS source current, this is IC capacitor current, and this is VC or capacitor voltage, and last one, that is the output current. So think about a first mode operation. When the switch is on, inductor starts storing energy and the current is gradually increases from its low value I1 to capital I2 during T1. And the voltage appearing across the load, that is Vs, this one. Okay. And when the switch is off, what happened? In the first mode operation, when the inductor gets charged fully with respect to the supply voltage Vs, then the polarity of the inductor was this one. Now in this mode operation 2, then the no supply voltage is given to the circuit. That means then the inductor tried to discharge and it has changed its polarity. Right? That means the inductor tried to discharge to freewheeling diode in this way. That means during charging and during discharging, the inductor current remaining same direction. And the current try to discharge. That means the current is gradually decreases from its higher value capital I2 to capital I1 in this mode during T2. So this is the operation. Next cycle will be repeated again. We are using the next triggering pulse to the switch, then the voltage appearing this one. Again the inductor tried to charge and the current is gradually increases for the next cycle. So that is why we can explain by the pictorial representation of the waveform, that is the output voltage and that is actually the inductor current. Okay. Now what about for IS? See, IS is here. That means in the first mode operation, the supply current or source current equal to IL, but in second mode operation, there is a no question for IS, only IL is there. That means IS is absent. That is why during T1 operation, this waveform should be followed here. That is why we have drawn this waveform. And during T2 operation, there is a no question for IS. That is why this is remaining 0. This remains 0. Okay. Again, the cycle will be repeated for the next half also. So this is all about for the IS. Now see, the dotted line is given here. That is called the average inductor current, that stands for capital IL, and here that is average IS, that stands for IS. That is why we have mentioned the IS part and IL part here. Okay, it is the average value. Now see, when the inductor starts storing energy from this point to this point and discharging from this point to this point, that means if we will consider this particular region, that means we can say this peaks, which is defined by this one, that is suppose, which is called actually peak to peak ripple current, that is defined by delta I. Okay, so this is all about for the waveforms. Next, consider IC is a very important part. Now see, if we can applying the KCL at this particular node, that means what? At this particular node, whatever, that means what? That is IL. It can be splitted by the two components. One is flowing through the capacitor and a different one is flowing through the load. That means we can say that is IL equal to IC plus I0. That means we can say IC equal to IL minus I0, right? That is why IC can be defined by IL minus I0. But as we know, the inductor charging and discharging path, the current across the inductor is gradually increases from some lower value, that is I1 to capital I2. That means IC should be equal to IL minus IA. That means I1 minus IA, again I2 minus IA, as we considered it is the high magnitude of the inductor current I2 and a low magnitude of the inductor current IL. That is why we can explain the term IC equal to IL minus IA. Same thing here. That means we consider this part. Here again we can consider this part, that is confined between the time duration T1 by 2 to T2 by 2. As it is T1 and this is T2, that means it should be T1 by 2 and this point should be T2 by 2. That means the peaks is confined the region T1 by 2 to T2 by 2. Okay, and this is the peak to peak ripple current of the capacitor. Okay, now go through this diagram. So before going into this means voltage appearing across the capacitor, so we should put an example here. Okay, unless we can not easily understand the thing. See, this is, I am putting an example here. Okay, just as we know the inductor current IL equal to IC plus IA. IA means the average output current and IC equal to average capacitor current. So we can say from this, suppose we assume two numerical values, that is suppose IA equal to 30 ampere and I1 equal to 30 ampere and I2 equal to 70 ampere. That means what? As we know, due to presence of the inductor, current is gradually increases from its low value I1 equal to 30 ampere to high value I2 equal to 70 ampere. And when the inductor try to discharge to the next cycle T2, then it start from 70 ampere to 30 ampere. Just assume this example. Okay. That means what? Now see, that will be reflected on the capacitor current. Okay, as we know the capacitor current magnitude is I1 minus IA and I2 minus IA, as the inductor current is I1 and I2. Okay, first think about, as we know this is a kind of chopper operation, that is why output voltage should be regulated DC, right? That is why assume the output voltage that is regulated DC, that is this is the constant magnitude of the output voltage. Assume this is suppose 50 ampere. That means what? We can assume all the cases during mode 1 operation and mode 2 operation the output current should be 50 ampere, as it will give us the DC part. Okay, it's a constant in magnitude. So if we consider this one, that means what happened during the inductor current and discharging and charging path. Now see, that means IC equal to what? That is I1 minus IA. That means we assume I1 is 30 ampere minimum and I2 equal to 70 ampere maximum at this point. That means in this point we can say IC will be, as I know, that is I1 minus IA, that will give you 30 minus 50, it will give you minus 20 ampere. That is why it has started from this point. Is a negative part. Okay. Similarly, that can again happen in case of this point. As we know, that is the point across this one, the capacitor current is I2 minus IA and the maximum I2 is 70 ampere and a fixed amount of DC average value, that is 50 ampere. That means it will provide you 70 minus 50, that means 20 ampere. That is why it has started from the positive part. Clear? Same thing was happened in the waveform, just I am verifying the waveform by a numerical example. Okay. So that means what? Now you can easily develop the capacitor voltage. Okay. See, that means what? Now going to the circuit diagram first. Okay. See the circuit very carefully. Okay. What happened? Okay. This one. See, we assume the inductor current is gradually increases from its low ampere 30 ampere to 70 ampere. It's true. And we assume the load always give us the constant magnitude of the DC, that is 50 ampere. Just I told you before. That means what? When the inductor current is gradually increases from its low value when the switch was in on state, then if it is 30 ampere, that means what? But as we know, 1 minute, if it is 30 ampere, that means what? See, okay, I'm taking a pen from here. That means when the switch is on, when the current starts gradually increases across the inductor, that is suppose 30 ampere, and as we assumed the constant magnitude of the output current is 50 ampere, that means what? The excess 20 ampere current which is delivered by the capacitor. Clear? Then the capacitor starts discharging, and which will provide, that is, additional 20 ampere current. That means this 30 ampere current and the capacitor discharging current suppose 20 ampere, then the voltage across the load will be 50 ampere. Okay. Now go to the next condition where the capacitor voltage, where the inductor voltage was maximum and which has reached suppose 70 ampere. Then what happened? Suppose when the inductor will have the maximum magnitude of the current, suppose is gradually increases from 30 ampere to right now 70 ampere, then what happened? But as we assume the magnitude of the current across the load is always maintained by the fixed value 50 ampere, that means what? This additional 20 ampere excess current which is right now flowing to the capacitor. Okay. And remaining means 70 minus 20, the remaining 50 ampere is current is delivering to the load. That is why the load current remaining constant 50 ampere. Okay. That means what? Right now the capacitor is storing energy in this mode operation. And in the previous one, when the load current is delivered from the capacitor, then the capacitor was in discharging mode. Right? Okay, I repeat one. Last time I'm repeating. See, that means when the inductor current is 30 ampere, but the remaining the current across the load is 50 ampere, then excess 20 ampere current is delivering from capacitor. Then the capacitor was in discharging in mode. When the inductor current is gradually increased to a maximum value 70 ampere, then the 50 ampere is delivering to the load and remaining 20 ampere is flowing to the capacitor. Then the capacitor starts storing energy inside it, or it is in charging mode. Okay. Though this operation can be well described by the numerical example. Now go through the example. Okay. That means now we are going to proceed the capacitor voltage. Okay. See, that means when the inductor current is gradually decreases from its maximum lower peak to 0, that means 30 degree, that means excess, that means it has started from 30 ampere. Here the inductor current is 0. That means inductor is gradually decreases from its negative current 30 ampere to 0. That means excess 20 ampere current is delivered from the capacitor, due to which in this particular region the capacitor was discharged, capacitor voltage falls. Clear? After what? Next, after crossing this point, then the inductor current is gradually increases from 0 to maximum value 70. That means what? When the current try to reach 70, then but the remaining constant current for the load part, that means excess 20 ampere current that is flowing through the inductor, then the inductor gets charged. That is why inductor voltages increases. Okay. Now consider the next part, means this duration. Again, due to presence of the inductor, the current is gradually decreases from 70 ampere to 0 ampere. Still, the capacitor still is charging mode because this excess current is delivering to the capacitor. That is why still the capacitor voltage is increased to the positive side. After this point, what happened? Again, the inductor current is gradually decreases from 0 to negative 30 ampere, means minus 30 ampere. Then the inductor current starts discharging, as now the discharging current 20 ampere excess current is delivering from the capacitor to the load. That is why the capacitor voltage is decreased. So this is the actual waveform of the capacitor voltage during charging and discharging mode. Okay, that can be easily reflected on this diagram, on this waveform. Just we have taken the mirror image or replica of this waveform from this one to this one. So we can easily understand how the capacitor voltage will give this kind of periodical wave shape. Okay, and the output voltage is constant and average output voltage is constant, that is 50 degree. Now we can easily understand the actual waveform of the circuit. Okay, now you can easily understand. See, this is the output voltage waveform. This is the inductor charging discharging current. This is IS, first mode operation present, next mode operation not present, 0. Then go through the IC or the capacitor current, just I explained before, that is I1 minus IA, I2 minus IA is the charging and discharging, and the respective capacitor voltage we can define by this waveform, and this peak to peak ripple voltage is the suppose that is del Vc. That means this peak to peak ripple voltage depends on the capacitor voltage as well as which is depends on the inductor voltage. Okay, so we can say this constant amount of magnitude of current which is appearing across load, that is depends on the charging and discharging of inductor and capacitor. That is why this LC is working as a filter to maintain the appropriate current in constant magnitude to the load. Okay, now go through the expressions, mathematical expressions. See, so the total operation can be replaced by the mathematical tools also and mathematical expressions also. So this is the all expressions I have done here. See, so first go to the first one. The voltage across the inductor L, that is the generalized form as we know from basic electrical, that is EL equal to L di dt. L is the inductivity of the inductor and that is the rate of change of current with respect to time or rate of change current. That means same thing can happen in the waveform. Inductor current rises linearly from I1 to I2 in the time t1. Then we can write the expression that is the potential difference across the inductor, that is Vs minus Va. Okay, that should be equal to L di dt, means the average current change with respect to, that means current change with respect to time, di dt. That means the current was changed from I1 to I2. That means current was gradually increases from I1 to I2. That is why I2 minus I1 by T1. So this is the expression which we can form from this expression. That is Vs minus Va equal to L into L into I2 minus I1 by T1. Similarly, from this expression, we can change the term, that is Vs minus Va equal to del IL by dt. As we know, I2 minus I1, that is defined by del I, which was mentioned in the waveform, that is replaced by del I into L by T1. So ultimately we will get the result del I equal to Vs minus Va into T by L, equation number 1. Similarly, from this equation we can again write the equation number 2, in which T1 equal to del I L by Vs minus Va. Similarly, we can do for the next case here. In the waveform, inductor current falls linearly from I2 to I1 in the time duration T2. That means in this particular case, as we know, there is no relation to the source to the circuit. That is why we can replace the part Vs equal to 0. That is why 0 minus Va equal to L I1 minus I2 by T2. In the first case, current was gradually increases from I1 to I2. That is why the expression was I2 minus I1. In this case, current is gradually decreases from I2 to I1. That is why the expression is I1 minus I2 by T2 during T2 time. Okay. That means after simplification, we can write minus Va equal to minus L I2 minus I1 by T2. And similarly, we can get the result Va equal to L di by del I by T2. As we know, I2 minus I1, that is defined by del I. So similarly, we can again derive the expression del I equal to Va T2 by L, equation number 3, and equation number 4, that is T2 equal to, that is del I L by Va. So as from these two equation, see the equation 1, see the equation 2 and see the equation 1 and the equation 3, we can write the expression as both are same, as both are defined by del I. So we can write the expression del I equal to Vs minus Va into T by L equal to Va T2 by L. So after simplification, we will get this result Vs into T1 minus Va T1 equal to Va into T2. Okay, we have take the common part here. That means again we can rewrite the expression like Va T1 plus T2 equal to Vs into T1. As we know, T1 plus T2, which is defined by the complete cycle capital T, so we can replace the term by T, and which will give the result, that is Va T into Vs into T1. So after derivation, again we can get, that is Va equal to Vs by T1 by T. Okay, as we know, T1 by T means duty cycle, which is defined by K. So the result is Va equal to T into Vs. As the all cases, the K always less than 1. That is why the output, average output voltage Va always less than Vs. That is why it is well defined by step down chopper or buck converter. Now for average value calculation of voltage, that is Va equal to K into Vs. If the system is lossless, then we can say Vs equal to VAIA equal to K into VSIA. And from this expression, we can deduce the expression Is equal to K into Ia. So the average output current, that is equal to K into Ia. Okay, and in this case again the average output current, that is multiplied by K term, and where the K equal to always less than 1, that is why it is step down chopper. Similarly, from the equation 2 and 3, we can write the expression, the switching period T we can express as t equal to 1 by f and t equal to t1 plus t2. And we take the value from these two equations. This is equation number 1 and the equation number that is 4. So put the result over here. So ultimately we can get the result that is 1 by f equal to del I by L Vs minus Va plus del I L by Va from the equation 2 and 5. So after simplification, we have that is Va del I L into L plus Vs del I L minus Va del I L, and the lower part is Va into Vs minus Va. After calculating, we will get the result that is this part is cancelled. Then ultimately we will get the result that is Vs del IL divided by KVS Vs minus KVS. Okay. Then further simplification, the result 1 by f equal to this one. See, in which we have taken the common part here. Okay. and we are replacing the part that is Va equal to KVS. So both are cancelled by each other. So ultimately we can reach the final expression that is del I means the ripple current that should be equal to peak to peak ripple current that should be equal to KVS into 1 minus K divided by F into L. Now consider the second thing. See, using Kirchhoff's current law that I have told before, that is IL equal to IC plus I0. That means we can say that is del IL equal to del IC plus del I0. Del I0 means is the very small change of output current. As the output current is DC component, that is why this change is very small in magnitude, near to equal to 0. That is why we will get the result that is del IL equal to del IC. Okay. After integrating both sides and taking the value of 0 to T by 2, as we know the average capacitor current which flows through for T1 by 2 to T2 by 2. So the summation of these two which will give you capital T by 2 means total time by 2. That is why we can replace the term over here. Okay. So after integrating both sides by the both purpose, that means the capacitor current IC which will give you 1 by T integration of 0 to T by 2 del I by 2 into dt. Fine. Now to further calculation, see, that means we can say del IC, we can say that this part means IC equal to 1 by T integration of 0 to T by 2 del I by 2 dt, just we have discussed before. That means here simple integration part T, that is integration that T, this is upper limit is T by 2, lower limit 0. By satisfying this one, so IC equal to 1 by T into del I by 2 into T by 2. This part will be cancelled by each other. So ultimately we will get the result that is IC equal to del I by 4. So this is the value of IC, del I by 4. Now we know capacitor voltage expressed as Vc equal to 1 by C integration of IC dt. It's a normal expression for the capacitor voltage in terms of IC. So we know the result IC in the equation 7. So the peak to peak voltage of the capacitor is, that is del V equal to, that is del V equal to Vc minus Vc at t equal to 0. That means this is the initial voltage at t equal to 0. because capacitor is always stored the few amount of energy inside it during the starting case. That is why, as it is working for the all cycles, that is the capacitor voltage initially, that is t equal to 0, there must have some magnitude, maybe 0 or maybe some another magnitude. That is why this is the expression. So after integrating, as we know, that is del 1 by c integrating of 0 to t by 2, that is IC, and we have taken the value of IC over here, that is del I by 4. Okay, so after simplification we get the result 1 by c into del I by 4 into t 0 to t by 2. That means we will get the result, that is 1 by c into del I by 4, and integrating this part we will get this result, that is t by 2. So after calculating the whole part, ultimately we will get the result C, that is kVs into 1 minus k by 8 f square Cl. This is the actual peak to peak ripple voltage across the capacitor. This is the expression which is defined by the expression, this one. Now the condition for the inductor current and the capacitor voltage, that means for designing purpose for the inductor and capacitor, so what will be the critical value of the inductor and the capacitor, that should be chosen during designing for the application of in industry. As we know, see, if IL is the average inductor current, the inductor ripple current will be, that is I del IL equal to 2 into IL. Similarly, if the VC is the average capacitor voltage, the capacitor ripple voltage should be VC equal to 2 VA. Okay. So right now, by satisfying this equation, we can write the expression, that is Vs into 1 minus k into k by FL, that we have deduced previously, that should be equal to 2 into IL. Okay, so after simplification, that means, as we know, that is IA means just a simplification, do the simplification part for this expression, then, and after satisfying the value of IA, that is equal to kVs by R, put the value over here, and ultimately we will get this result. IC as a critical value of the inductor, that is L equal to 1 minus KR by 2Fs. So this is the value of the inductor. Okay. Similarly, for this purpose, that is KVS, that means, as we know, that is del VC, just we have derived before, that is KVS 1 minus k by 8 f square Cl, that should be equal to VA, as we know the result of VA, that is equal to KVS, just put the value of the result of VA, then after simplification we will get this result, that is capacitor, the critical value of capacitor CC or C equal to 1 minus k by 16 f square L. Okay, so this is the critical value of the capacitor and inductor, through which we can design the total converter part, or the buck converter, through which we can get the good quality of output and regulated output. So this is all about for the buck converter or buck regulator. Okay, thank you.